Hello, my Algebra 2 students. It's day 8 of Unit 11, and we are talking about half-lives. I'm imagining you've probably talked about them in science before, but if you don't know, the half-life of a radioactive substance is the time required for half of the given sample to disintegrate. So the half-life doesn't depend on how much you start with, it just depends on how much time has gone by as to how much you have left, all right? So it's saying if the half-life of a certain substance is known, scientists can determine how old a given sample is based on how much is left. So here's a little example. It says, suppose the half-life of a certain substance is known to be 3 days. If there's initially 10 grams of the substance present, determine how much of the substance remains in each of the days listed. So day 0, meaning you have all 10 grams in there. If one half-life is 3 days, then 3 days later, you should be down to half of the initial substance. And then another 3 days goes by. Now you'd be half of what you had. And you could keep doing this. So we go to 9 days in. Now it's half of that. So half of 2.5 would be 1.25. Where it gets tricky is what happens when it doesn't jump by a half. So for something like this, it's a little bit of a question mark. So we want to look at, as it says, determine the amount of a given substance at any time t would be helpful. All right, well, if we think about what was going on back here, is that at day 0, the amount that you had was just the 10 grams. At day 3, you took that and multiplied it by a half, and it came out to be 5. At day 6, we multiplied it by a half twice, or 1/2 squared. That's where the 2.5 came from. By day 9, you'd have multiplied it by another 1/2. So 1/2 to the third power, that gives us the 1.25. So what it might be easier to do is think about it as how many half-lives have gone by. So here, 1 half-life, 2 half-lives, 3 half-lives. Well, to calculate the number of half-lives, what you have to think of is it's how much time has passed divided by the length of the half-life. And so how I really want to think about that would be to write it in a slightly different way. So I'm going to slide this up here. What we can say is, in general, that the amount that will be left is based on, all right, well, what did you start with, times 1/2, raised to the amount of time that's gone by, but then divided by the length of the half-life. Which hopefully makes sense when you look at these, because that would have been 3 days divided by 3. That would have been 6 days divided by 3. This was 9 days divided by 3. So in general, number of days or the amount of time divided by the half-life. So let's just clarify. This is the amount remaining. P is always that principal amount, or we can say initial amount. T is time. It'll depend on days or years and so on, depending on the context of the question. And then H is the length of the half-life. So if we look back at that last part to then figure out what would be the amount remaining after 10 days, we can say 1/2, and then it would be raised to the 10/3. So you have that fractional exponent. And then we could go to the calculator. So 10 times 1/2, and then raise it to the 10/3 power. It would have been about 0.99 grams remaining. Cool. Let's keep moving. So now that we have a formula, we can use it. So this first example says one of the medical uses of iodine 131, a radioactive isotope of iodine, is to enhance X-ray images. The half-life of I-131 is approximately 8.02 days. So that would be the H value in the formula. The patient is injected with 20 milligrams. That's how much we're starting with. And it asks to write an equation that can be used to represent the amount of I-131 remaining after T days. So we're going to keep A, keep T, plug in for H, plug in for P. So 20 and then times 1/2 raised to the t over 8.02. That's the equation. Part B, how much I-131 remains after 2 weeks? Be careful of the unit of time. So up top, they were talking about days. Here we're talking weeks. We want to change this into days. So after 14 days, we can then plug in t equals 14 and calculate. 20 and then times 1/2, raise that to the 14 over 8.02. So 5.96. And this would be milligrams. And hopefully if we stop and think, 1 half-life is about 8 days. So that would have been from 10 down to, 20 down to 10. And then this is almost a second full half-life. So that would have brought us down to 5, so not quite 5. All right, part C, determine to the nearest day the amount of time needed before the amount of iodine in the patient's body is approximately 7 milligrams. So it should be a little less than what we had here. But we want to find T given that A is 7. So 7 goes in on the left, 20 times 1/2 to the t over 8.02. We're going to use the calculator to solve this. We can go right now to y1, y2, or you can divide the 20 out and go to y1, y2. Sometimes it's nice to divide the 20 first. I'm actually just going to leave this as 7/20 or 0.35, either way. And then I have 1/2 to the t over 8.02 power. All right, y1, y2. So 0.35 and then 1/2 raised to the t, or in this case, x over 8.02. Now, when I go to graph it, I'm going to start with zoom 6. But what you're going to see is that line is so close to the x-axis that it's almost tough to get a read on what's going on there. So what I would suggest is let's zoom in a little bit by adjusting the window. So I'm going to make the y minimum 0 and the y max 1 because my y values are right between 0 and 1 here. So if I hit graph, now I can see things a little bit better. Right, and I can see it's not intersecting yet. So I'm going to take my x value and change it from x max of 10 to an x max of 20. And so when I sketch it, I want to show that. So I'm showing 0 to 1 and then 0 to 20 on my x-axis. So then I can see here's my y1, there's my y2. And anytime we solve graphically, second, trace, intersect, get as close as we can and enter, enter, enter. So that point, x comes out to be 12.14 and it keeps on going. And so it says to the nearest day. So since x is our time, this would be approximately 12 days. All right, example number 2. This time we have iridium 192. It's an isotope. Half-life is 78.83 days. A laboratory experiment begins with 100 grams, which equation approximates the amount that would be present after t days. If you look at all of these, none of them are quite set up the way that we are used to, meaning that if we plug in p for 100, then 1/2 raised to the t over 78.83, because that's our h value. So if none of them quite match, we have to rearrange. And this goes back to what we learned a little earlier in the unit. we can get this back into a more standard form by breaking this up and saying that this is the same as 1/2 raised to the 1 over 78.83, and then all of that raised to the t power, because power raised to a power, it would bring me right back here. So now I can take this part and clean it up in the calculator. So if I do 1/2 and then raise it to the 1 over 78.83, that'll give me 0.9912, and of course it keeps going. But the question said, which equation approximates the amount? This one is really darn close to this guy right here. That is the best approximation of what's happening. All right, next up. This one here says we have a picture supposedly painted by Vermeer, who lived from 1632 to 1675, and it contains 99.5% of the carbon-14, where the half-life is really big, 5,730 years, saying from this info, determine whether the picture is a fake. So this one's different in that it tells us what percent of the the carbon is left. So what we have to think of is what we started with would be 100%, and then the current amount would be 99.5%. The H value is 5,730, and then we want to know how much time has passed. So we're looking for the T value. So let's plug in. I'm not going to use the percent. I'm going to drop that as I plug in here. The same way you would drop grams or milligrams. We don't need it. All right. Now you can go right to just putting this into Y1 and Y2. In that case, I would have to change my window to see up to 100, or I can divide the 100 out, and then we can kind of keep the window from the last problem. So 99.5 divided by 100 is just going to move the decimal. So 0.995. This will drop the 100, and then 1/2 to the T over 5,730. Y1, Y2. Go right back in, delete out the last problem, and let's put in 0.995 and then 1/2 raised to the x over 5,730. If we remember from the last problem, it goes from 0 to 1 and 0 to 20. If I just hit graph, I can see that line. Ooh, and I can actually see the red exponential coming in, but it is not zoomed in enough. So let's go change the window a bit. So up here, I'm going to change my y minimum. Instead of being 0, let's get a lot closer. Let's put like 0.9, and then my maximum, let's leave it at 0.1, and just hit graph. All right, so two things are clear. One, I'm still not close enough on the y's, and I need to move over further on the x's. So I'm going to change this up again. Let's make the x's bigger. Let's maybe go out to 100 on the x max. And then on the y minimum, let's move that up. Let's make it 0.95. Let's get a little closer here. Now we're talking. Now we can see what's going on. So in case you missed my window, I am from, on the y-axis, from 0.95 up to 1.0, and then on the x-axis, I'm going from 0 to 100. So when you see my graph, here's my y1, and there comes my y2, that decreasing function, because the amount is going down, and then my intersection point. So it doesn't have to be the most beautiful window. You just have to be able to see it so that you can calculate the intersection. So second, trace, intersect. So as a reminder, second, trace, intersect. I'm coming out with 40.83 is my intersection. So that's my x value. All right, let's bring it back to the question. It was asking us, is it painted by this painter or is it a fake? So based on this, the amount of time that has passed, because x is representing time, has only been about 41 years. And so if it's only 41 years old, could it have been painted back in the 1600s? No way. This is definitely a fake. Whew. All right. On to the next page. Example 4, we're going to skip. So let's save that guy for class. And then the last question that we are going to look at today is actually a little different. It's example 5. And it's not a word problem. It's just some graphing practice. So for this particular one, you're just simply being asked to graph it over a particular interval. So again, it means we have to make sure to set a nice window on our calculator, but we're going to put all that into y1. So let's go back to clear out what we had, and into y1, 400 times 0.85, raise it to the 2x, and then minus 6. If I look at the scale on the graph that's shown here, that'll help me set my window. So I want this to go from 0 to 10 on my x scale here. And then on the y scale, it looks like 0 up to 400. So if I hit graph, I get an idea of what we're going to be graphing here. So it's a decreasing function. That 0.85 makes sense because that's less than or between 0 and 1. All right. But now it says specifically graph it between 1 and 10. So I would go to my calculator and look at the table of values. Starting at 1, it's at 283. 2 is 202.8. 3, we've got 144.86, and so on. I would write all of these down and then plot them on the graph. And I realize some of them have some fairly obscure decimals attached. When you go to plot them, you're just going to do the best you can. Oops, little goof on that last guy. So it starts at 1 and then 283. So keep in mind, if this is 100, so 1, 2, 3, 4, 5, 100 divided by 5, each line is worth 20. So then 1, 2, 3, 4, 5, there's 200. 1, 2, 3, 4, 5, 300, and so on. So 283, so this would be 280 right here at 1, just a little bit beyond that. And then at 2, looks like every 2 lines is representing one single unit on the x-axis. We're just at 202, so a little bit over 200. At 3, we're at 144. At 4, we're at 103. So take your time, plot out all the points nice and neatly. And what you should be able to do by the end of it is connect the dots in a fairly smooth curve. That's your goal. So starting at 1, going to 10, when the directions specifically say graph from here to here, that means we're going to have endpoints on the graph. So resist the urge to put those arrows on the end. We want specific endpoints. And done. Thanks, guys, for watching.